Hello everyone. In this lecture, I will discuss the applications of handshake lemma. In the previous lecture, we saw that handshake lemma. What was the handshake lemma? A sum of degree of all the vertices in a graph is even and is equal to the twice number of edges in that graph. Okay, so this is in a theorem which is the application of in a handshake lemma. So theorem is saying that in every graph the number of vertices of odd degree is even. So how can we prove this theorem? So proving this theorem, we should know the handshake lemma. So basically, let us suppose that we have an n vertices. We have a graph Z, and this graph Z has n vertices. Okay, so we have two types of vertices. Some vertices are even degree and some vertices with odd degree. So I am taking here V1, V2, Vk vertices are of even degree. These vertices have even degrees, and Vk plus 1, Vk plus 2, so on Vn. These vertices are odd degree. Okay, and we have total vertices are n vertices. So by the handshake lemma, handshake lemma is saying that degree, the sum of degree of all vertices is that twice of the number of edges. So basically T of Vi equal to I equal to 1 to n equal to 2 into q, where q is the total number of edges in that graph. So here we have vertices of even degree and odd degree. So we can break this summation into two parts. First part is the degree sum of even vertices, and second part is degree sum of odd vertices, that equal to 2q. So here we can say that this is even degree, sum of even degree vertices, so that factor will be always even number. So we can say from here degree of Vi equal to 2q minus, if we can say that this number is small p, so 2q minus p, and p is an even number. So here we can say that some degree of odd vertices is even number. This is also an even number. So what is the mean that from here we can imply that the number of vertices of odd degree is even. Okay, because we will do the odd degree v1 plus v2 plus degree vk plus 1 vk plus 1 are odd, odd plus odd plus odd plus, because degree of v1 is odd, vk plus 1 is odd, vk plus 2 is odd, plus odd plus odd plus equal to even. So how many times we can add the odd numbers will get the even numbers? So we have to add odd numbers in even times. Okay, so that will come from here. We can directly imply that the number of vertices of odd degree is even. Okay, so next is concept is related to the degree sequence. Degree sequence is like that a finite sequence d1 d2 dk of the non-negative integer is called degree sequence of the graph Z if the vertices of Z can be labeled as v1 v2 vk such that degree of vi equal to 4 always. Let us suppose that we have a graph v1 v2 v3 v4. So degree of v1 is 3, degree of v2 is 3, degree of v3 is 2, and degree of v4 is 4, because loop is contributing degree 2. 2 plus 2 4. So we can write in the format of the sequence, and basically this sequence is no in decreasing form. First of all we write the is degree and v4, then after 3, then after 3, then after 2. So basically it is in a decreasing sequence of in a degree sequence. So next, a small numerical example. Is there a simple graph with degree sequence? Can we construct a graph with degree sequence? Means we have a vertices 2, 3, 4, 5, 6, 7, 8 vertices. We have total 8 vertices with these degrees. So we can construct a graph. So this is that I will choose a vertex v1 that have degree 7. So that will be connected to 7 vertices. Okay, 3, 3, 6 and 7 means v2, v3, v4, v5, v6, v7, v8. Okay, now I will choose a one vertex which have degree 6. So from here I will choose a vertex v2 which have degree 6. So it will be connected to each all vertices except vertex v1. Okay, so all the vertices up to here we can see that each one vertex have degree 7, degree of v1 is 7, degree of v2 is 6, and all other vertices, remaining vertices have degree equal to 2 up to here. But here we can, in the degree sequence we are looking this degree 1 is also there, so this type of the graph is not possible, it is in a contradiction. So this was a numerical example. Next is a definition of a complete graph Kn. So what is the complete graph? A graph G on n vertices is called a complete graph if all the vertices are adjacent to each other. Each other means we are taking, if we are taking 4 vertices, so the definition is saying that we have 4 vertices, so each vertices all the vertices are adjacent to each other, means this vertex it is a v1, so v1 is adjacent to all other vertices. Okay, so this vertex is v2, v2 is adjacent to all other vertices. Same for v3, v3 is adjacent to all other vertices. So this is in a complete graph. Okay, means each vertices is adjacent to all other vertices is called a complete graph Kn, where n is number of vertices. Generally it is denoted by Kn, so it is graph of K4. Here we can make an K5. We have 5 vertices and each vertex is connected to all other vertices, so it is a K5. So from here we can see one observation that the degree of each vertices have same. Here we can say that the degree of this vertex is 3, the degree of this vertex is 3, degree of this vertex is 3, degree of this vertex is 3. Here we can also see that 4, 4, 4, degree of each vertices is 4. If we have 5 vertex, then degree 4. If we have 4 vertex, which have degree 3, means we have n vertices. So if we will choose one vertex, so this one vertex will be adjacent to n minus 1 vertices. Okay, so here from we can see that a complete graph is a n minus 1 regular graph. This is also an observation. So next observation is that every complete graph is n minus 1 regular, means if we have n vertices, so that degree of each vertices is n minus 1, so we can say that complete graph is n minus 1 regular. Okay, next observation is that the number of edges in a complete graph Kn of order n means we have n vertices, is nc2. nc2 is basically n into n minus 1 divided by 2. So here we apply this, total number of edges in the complete graph is n into n minus 1 by 2. So here we have an edge 1, 2, 3, 4, 5, 6, means 4c2, 4 into 4 minus 1 by 2 equal to 6. Okay, so how can we find this total number of edges in a complete graph? So I will give an hint how can we write by the help of an examples. Let us suppose that this is in a combinatorial approach. We have 4 vertices and each vertex is connected to all other vertices because this is in a complete graph. Okay, so here we can say that sorry, it is so we have these 4 vertices and each vertex is connected to all other vertices. Okay, so v1, v2, v3, v4. Okay, so we have n vertices. Okay, so I will choose one vertex that will be connected to n minus 1 vertices, that will be connected to n minus 1 vertices. Okay, because complete graph is n minus 1 regular. So I will choose v2, that vertex is also connected to n minus 1 regular. Same for v3 is connected to n minus 1 regular. So we have, what is the choice up to vn? Because we have total vertices is n, we have n choices are n minus 1 regular, so total number of edges is n into n minus 1. Okay, but some vertices are repeating, because if v1 is connected to here v2, so v2 is also connected to v1, so they are repeating, so we will divide by 2. Okay, so basically this is in a combinatorial approach. We are making the possibilities, means we have one vertex v1 that will be connected to n minus 1 vertices. Second, v2 is connected to n minus 1 vertices, so we have total vertices n. So what will be the number of possible ways? N into n minus 1. But here some edges are repeating, half edges are repeating, because v1 is connected to v2, v2 is also connected to v1. Same for v3, v1, here v3, so v1 is connected to v3, but v3 is also connected to v1, so these are edges are repeating, so we will divide by 2. So hence we have in a complete graph kn with n vertices, so total number of edges in complete graph will be nc2, which is equal to n into n minus 1 by 2. Okay, so we can also this proof of this observation by the help of handshake lemma, so I am not discussing here. Okay, thanks.